given a function of several variables to r, we can define now an integral over a curve. So we have defined it before in this kind of functions, integrals over domains in the two-dimensional space. We are defining now an integral over a curve. So to calculate the integral over a curve of a function like this, we are going to evaluate the function at the curve. I mean, if we have given the curve by this parametrization for certain values of t, so we are going to evaluate the function at the curve, and we are going to multiply by the norm of the derivative of the curve. So we know that given a curve, we know how to calculate the derivative, right? It's the derivative of each component. And so having these two, having this vector here, we are also able to calculate the norm. So we evaluate the function at the curve, we obtain a numerical expression, and we multiply by this other number that will be the norm of the derivative of the curve. For example, let's calculate the line integral of this function over this curve. So in this case, the function, if we want to write the function explicitly, the function that we are integrated is a function from R2 to R, such that to each value of xy assigns x squared y plus 1, right? So this is what this function f is. And the curve is given already with a parametrization here. This is a circle, this is a part of the circle where t vary between 0 and pi. So this is, if we do the sketch of this curve, this gives half of the circle until here, and traverse in this direction. Okay, so according with the definition that we just saw, we are going to need, besides the curve, we need to have the derivative of the curve. So we do that, we calculate the derivative of the curve. That will be the derivative of cosine, which is minus sine, and the derivative of sine, which is cosine. And once that you have the derivative of the curve, what we need is the norm of this derivative. So to calculate the norm, so we just do the square root of the first component square plus the second component square. Well, in this case, this is just the root of sine squared plus cosine squared, that is the root of 1, which is 1. So we got then the norm of the derivatives, that is one of the things that we need inside of the integral, and we need also the function evaluated at the curve, which is this one here. So let's do that too. So let's calculate the function evaluated at the curve. So the function is this one, and we have to take now as x, y, the values of the curve. So in the first thing to evaluate here is x squared, so then we're going to put here cosine squared times y. Well, y is sine of t, so that will be times sine of t, and then plus 1. Okay, so that will be the evaluation of the function at the curve. So we have then the two things that we need to multiply, right? This numerical expression and this one. So the line integral will be the product of these two. So the line integral will be the integral from 0 to pi of this one here, which is cosine squared of t sine of t plus 1 times this one here, that in this case is just 1, and dt. Okay, so let's calculate this integral. So we can do, in order to calculate the primitive of cosine squared of t sine of t, we can do a change of variable, and we deduce that by doing a change of variables. we get that the integral of cosine of t sine of t dt is just minus cosine cube t over 3. This is just doing a change of variable. We can calculate this primitive. So once that we have this primitive, so then we come back here, and this then will be equals to, and we use the primitive here. So that will be the primitive of this part will be minus cosine cube t over 3 plus the integral of 1, which is t. And this will be evaluated between 0 and pi. Let's evaluate at pi first. So evaluating at pi, we will have minus 1 over 3 minus plus pi. This is the whole expression evaluated at pi. And now we subtract now the whole expression evaluated at 0. So that will be here, cosine of 0 is 1, so that will be minus 1 over 3, and then plus 0. Okay, so here we get that this is equal to 1/3 plus pi plus 1/3. At the end of the day, this is equal to pi plus 2/3. So this is then the line integral of this function over this semicircle. So let's do another example where the function has a domain in R3 instead of R2, and the curve is also a curve in R3. So let's calculate the integral of this function now over this curve where the variation of the parameter goes between 0 and 3. Again, what we need is having the curve, we need to calculate the derivative of the curve, that in this case the derivative of t is 1, derivative of minus t is minus 1, and derivative of phi t is 5. And then what we need of this is the norm of this vector, which is the square root of the square of 1 plus the square of minus 1 plus the square of 5. And so this makes the square root of 27, that is 3 square root of 3. Okay, so this is then the norm. I mean, the 3 square root of 3 is the norm of the derivative, that is part of what we need inside of the integral. And we need also the function, that in this case, this is a function that depends on x, y, and z, and is equal y squared plus xz, right? So that's what we have given here. So this function needs to be evaluated now at the curve, that is the one given here. So the function evaluated at the curve will be y squared, where the y is minus t, so that will be minus t squared, plus x, well the x is t, times z, well z is phi t. So the expression is then t squared plus phi t squared, 6t squared. So we have then the two functions, the two numerical functions that we need to put inside of the integral. We need to multiply these two. So the integral over c So the integral over c of this function is going to be equal to the integral from 0 to 3 of, and what we put inside is the function 6t squared times 3 square root of 3 dt. And so, putting all the numbers outside, this is going to be 18 square root of 3, and the integral of t squared, which is t cubed over 3, evaluated between 0 and 3. So 18 over 3 is 6, so then this is going to be 6 square root of 3 t cubed evaluated between 0 and 3. So this is c square root of 3 and times t cubed, which is 3 cubed. And so this is the result then of this line integral. So besides calculating integrals of functions, we can also calculate integrals of vector fields. So we're going to define the line integral of a vector field along a curve as this integral here. What we're going to do is to evaluate the vector field at the curve. That would be the same way that we did it with functions, right? But now in this other function, which is a vector field, we are going to evaluate the vector field at the curve as before. But remember that now this is a vector field, so the result of the evaluation is going to be a vector, not a number as before. And we are going to have here the derivative of the curve. So now is not the norm, but the actual derivative of the curve, meaning a vector with three components, or two components, depending on what space we are. But in any case, we are going to have here a vector and another vector. So this dot that is here is not multiplication of numbers, it's the dot product of vectors. So this is going to be then the definition of a line integral of a vector field. Evaluate the vector field at the curve and do the dot product with the derivative of the curve. An alternative notation, by the way, for this, if we consider the vector field that have in the two-dimensional space with two components, so we can write this one as the first component dx and the second component dy, where the dx and the dy are just the components of the derivative, the first and the second component of the vector derivative. So for instance, let's calculate this integral here. So this integral is the integral of now a vector field, right, that has these two components, and this is the curve. Well, as before, we are going to need to evaluate the function at the curve. So let's start by doing that. So this is the vector field. This vector field take each x, y, and transform in the vector minus y, x. Well, if we evaluate this at r of t, at this, where this is going to be the x and this is going to be the y, so now the result is going to be here minus y. Well, the y is this, so then it's going to be minus sine t. And then the second component is just x. So, well, x is cosine of t, so then it's going to be cosine of t. So we got then the evaluation of the vector field at the curve. And this is the first of the vectors that we need for our dot product. The second one is going to be just the derivative of the curve. So let's calculate the derivative of the curve. So the derivative in this case, the derivative of cosine is minus sine, and the derivative of sine is cosine. Okay, so we have already then the other vector that we need in order to do the dot product. So then the integral over the curve of the vector field dr is going to be equal to the integral from 0 to pi half. Of what? Well, the dot product of this with this. So let's calculate this dot product. Remember, dot product means to multiply first with first. In this case will be minus sine t times minus sine t plus second with second. In this case will be cosine t times cosine t. Okay, and in this case we can see already that this is sine squared plus cosine squared, right? We got a very easy integral here. This is just the integral of 1 dt. And this is then, the integral is t, evaluate between 0 and pi half, so the result is pi half. So we got that the line integral of this vector field over this curve is equal to pi half. Let's do another example with 3 components. So let's see, in this case the vector field is this, in this case the curve is this. We're going to do exactly the same. We're going to calculate the vector field evaluated at the curve, and when we're done with that, we're going to calculate the derivative of this, and we're going to do the dot product between them. Let's evaluate the vector field F at the curve. This is going to be, so the vector field is this one, right? So the first component is z. So plugging in z here will be just t. The second component is just x. X is t squared. And the third component is y, that in this case is square root of t. Okay, so we got the vector field evaluated at the curve. This is the first of the vectors that we need for the dot product. And the second one is going to come from the curve. It's just the derivative of the curve. So the derivative is going to be, the derivative of t squared is 2t. The derivative of square root of t is 1 divided 2 times square root of t. And the derivative of t is just 1. Okay, so we got the second vector that we need in our dot product. And so the integral of the vector field over the curve is going to be just the integral from 1 to 4 of the dot product of these two things. So that is going to be, in this case, t times 2t plus t squared times 1 over 2 square root of t plus square root of t times 1. Okay, and now it's just doing the operations here, simplify and integrate. So that is the integral between 1 and 4 of 2t squared plus, so here we have t squared divided t to the 1/2, right? So then we can say that subtracting there, so we get that this is t to the 3/2 over 2, and plus here is just t square root of t, or t to the 1/2. If we want to write it like that, it will be easier to do the primitive in the next step. And so, doing the primitive here, this will be the primitive of 2t squared will be 2t cubed over 3 plus the primitive of t to the 3/2 will be t to the 3/2 plus 1, which is 5/2 over 5/2, and times this 2 that was already there, and plus the integral of t to the 1/2, that will be t to the 3/2 over 3/2. And all these should be evaluated between 1 and 4. So let's simplify first. So this is 2t cubed over 3 plus 2 and 2 cancel. This is a square root of t to the 5th power over 5, and so plus this gets reversed, and so this is 2 square root of t cubed over 3. And this is what we need to evaluate between 1 and 4. So let's start the evaluation here. Let's evaluate first at 4. Evaluating here, substituting t by 4, we get here 2 times 4 cubed over 3 plus 2 to the 5th power over 5 plus 2 times 2 cubed over 3 minus, and so we evaluate everything at 1. That will be just 2/3 plus 1/5 plus 2/3. Okay, in order to do this operation, I observe that in all the terms there is a common factor that is 2 to the 4th power. So we can take 2 to the 4th power as a common factor, 2 to the 4th power, and if I take 2 to the 4th power there, remains inside just 8/3. Plus, if I take 2 to the 4th, remember, just one of the 2's there, divided by 5. And if I take 2 to the 4th here, remains just 1/3. minus this addition here, that will be just 23 over 15, right? So doing the common denominator here, 15. Okay, so let's continue this operation. This is 16. Doing the operation inside here, we get 51 over 15 minus 23, 15. Okay, and multiplying here, 51 by 16, we get 16 minus 23 over 15. So the final answer is 793 over 15. So this is then the value of the integral of the vector field. And finally, some applications and names that come mostly from physics. It's called circulation of the vector field along a curve, what we just calculate. Just the line integral of the vector field is what is called the circulation. And we can write it also with this alternative notation, just PQ, as we have seen before. But the flux of a vector field along a curve is, instead of multiplying by the tangent vector, we are multiplying by the normal vector. So because of that, we are going to get an inversion of the signs here, and the result is going to be just this component negative dx and the first component dy. Let's calculate the flux of the vector field to x to y over the circle, over the unit circle traveling in this direction. So we know that the parametrization of the circle is RT equal cosine t sine t, where t vary to get the whole circle between 0 and 2 pi. So to calculate the flux, then, we need to calculate the integral, as was said before, of minus q. I remind you the formula. The integral was minus q dx plus p dy. So we're going to need all the same things that before, right? To evaluate the vector field, to calculate the derivative, but we are going to, at the end of the day, calculate this integral instead. So let's evaluate the vector field at R as we do always. So that will mean to substitute here the x and y by the components of R. So in this case will be 2 cosine t and 2 sine t. So that's the evaluation of the vector field at the curve. And the other thing that we need, as always, is the derivative of the curve. So in this case, the derivative of the curve is minus sine, and the derivative of sine will be cosine. Okay, so we have the two vectors that we are going to need, but we are going to arrange them in this way to calculate the flux. So we are going to start by minus q, which means like the second component of the vector field negative. So that will be minus 2 sine t. And then this is going to be multiplied by the first component of the derivative. So this is going to be minus sine t. And then plus, we're going to put p, which is just the first component as it is, 2 cosine t, multiplied by dy, the second component of the derivative, which is cosine t. And so we're going to do this dt between 0 and 2 pi. Okay, so now let's simplify. This will be equal to the integral between 0 and 2 pi of minus and minus is going to be plus 2 sine square of t plus 2 cosine square of t dt. So we have again 2 that is a constant out. The integral of 1 is t evaluated between 0 and 2 pi. So then this is going to be 2 times 2 pi. So the flux is going to be equal to 4